I'm from the National Polytechnic Institute from Mexico, and today I will be presenting the development of a wireless electrogastrography measurement system. As an introduction, gastrointestinal diseases contribute to approximately 1.4 million deaths annually in the world, being the low-income and middle-income countries the most affected. In Mexico, these diseases are one of the most common health problems in the public health institutions and take approximately 20% of the outpatient consultations. So, considering this, there have been developed several techniques for the diagnostic of these diseases. We can divide them in two. First, we have the invasive ones. For example, the endoscopic studies, the esophageal manometry, the pH monitoring. And for the non-invasive ones, we have the laboratory tests and, of course, the electrogastrography. The electrogastrography is a non-invasive and cost-effective technique that allows the user to measure the myoelectrical activity in the abdomen with cutaneous electrodes placed in the abdomen, like in this photo. The features of our signal are a frequency of about 8 millihertz to 0.15 hertz, an amplitude from 40 to 500 microvolts. And we have two main artifacts. First, we have the respiratory cycle, and then we have the heartbeat, as we can see in the figure. The problems that we found in this area was that we have commercial devices that are not really optimized for these applications. The circuits that we can use for this are general purpose via data acquisition systems. So we need solutions specifically for these systems, for the electrogastrography systems. And there is a lack of public databases to analyze these results, and we can develop more diagnostic techniques, or maybe develop of AI-based diagnostic tools, for example. Here is our solution proposal. We have a circuit composed by these stages. First, we have our preamplification stage that is coupled with a driver and right leg circuit. Then we have a filtering stage, an amplification stage, and then we have our signal conditioning circuit to convert our signal from analogical to digital. And then we have our microcontroller and a wireless communication system to visualize and storage our information. So first, we have our preamplification part. We used an INA 122 to acquire the signal direct from the electrodes, and coupled with that, we used a driver right circuit. Here we used a gain of 1000. Then we have the filtering part. Here we used two filters. First, we have a high-pass filter with a second-order Bodenburg filter with a cutoff frequency of 0.0159 hertz. And then we used a low-pass filter that is also a second-order Bodenburg filter with a cutoff frequency of 3.121 hertz. Then we have the last three stages. We have the post-amplification stage with a non-inverting amplifier. Here we used a gain of 10, so it gives us a total of 10,000 as an amplification. Then we have the signal conditioning. We are using an analogical to digital converter, the ADS 1115. That is a more precise ADC than we can find in the SP32, that is our microcontroller. And it allowed us to measure a signal in positive and negative range. Then we have our microcontroller. We are using an ESP32 for its characteristics. We can use it wirelessly with Bluetooth or Wi-Fi. We are using Wi-Fi in this case, with a sample rate of 4 Hz. And we are using to transmit that information, the UDP. We designed a printed circuit board for this application. We have all the stages that we previously viewed here. And we are adding a connector for the electrodes and for the power supplies. The next stage was the development of a graphical user interface. We have 5 parts mainly. We have an start button and stop button, an export button that we can export the information, the record of the volunteer in this case, to an Excel archive. And we have an indicator that say to us if we are recording the signal correctly. And we have the main plotting area where we can see our signal in real time. So, as an experimental results, first we have the data collection. We developed a protocol to record this data. We did it for 20 minutes, for 10 minutes, sorry, and we did it with 10 healthy human volunteers. The procedure was briefly the following. First, we asked some questions of interest for the volunteer, like their age, their gender, and if they are healthy or non-healthy. In this case, we only use healthy. Then we ask the volunteer to lie down on a stretcher to record the signal, because when we are sick, maybe we can have some the belly of the stomach maybe it may not allow us to measure correctly. Then we disinfect the abdomen skin with alcohol and cotton. And the last part was placing the electrodes and record the signal for 10 minutes. So we have 10 recorded signals, and the process to signal processing was the following. First we have the raw signal, then we digital filter the signal with an IIR, high pass and low pass 10th order Butterworth filters with the same cutoff frequency than we used in the analogical filters. And then we normalized the signal from 0 to 1, considering the maximum of all the signals and the minimum of all the signals too. We obtained the following main components with the FFT. We divided the analysis too in 3 sections, considering our main frequency of the EGG, then the principal 2 artifacts that we have, the respiratory cycle, and then the heartbeat. So we obtained the following. Our maximum was first in 0.055 Hz, that corresponds to the main frequency of the EGG. And then in the window 2, we have 0.32 Hz that corresponds to our respiratory cycle. And the last one, 1.138 Hz that corresponds to the heartbeat. For the data analysis, we computed the power spectrums of each signal, and we calculated the mean and the standard deviation. So we can see it in this plot that we are seeing the first window, and we are obtaining the maximum of the power here in this range that corresponds to the AGG signals. So it's a technique for validation that results. And then we have the artifacts. We cannot see really a high frequency or a high peak in the values because we are filtering, so we don't have really that analysis like in the last one. And last, we have the conclusions. The proposed system accurately captures gastroscopic electrical activity, as we could see. Many EEG frequency components were founded in these results. This enables consistent collection and opens the door to create a public database, and with that database, as a future work, we can develop more diagnostic techniques. And that's all. Thank you.